We will now go over an overview of the matrix factorizations which will help us in solving linear systems of equations, linear least squares, and also instability analysis. Let us first consider solving the linear system AX is equal to B where A is a square matrix. For a general matrix A, this can be difficult to solve. Our approach is that we would like to decompose A into the product of some matrix B times some matrix C. Then we can define a vector y to be cx and first solve the system by is equal to b, and then solve cx is equal to x for our solution vector x. Why has this simplified our equation is that if we choose b and c such that they have specific matrix properties, we have reduced our hard problem in equation 1 to 2 easy problems. What structure would we like B and C to have? We have already seen examples of matrices that are easy to solve with, such as diagonal, triangular, or orthogonal matrices. For this example, the LU factorization would work well because B and C are upper and lower triangular matrices. Another example would be setting A is equal to QR, where Q is an orthogonal matrix and R is an upper triangular matrix. Now we will look at the case where we're trying to solve a linear least squares problem. Here, A is no longer a square matrix, but it is a rectangular matrix with more rows than columns, so M is equal to N. We no longer have a solution, and so we must minimize the residual subject to some norm. For least squares, we are minimizing the 2 norm. In a minimization problem, we must first choose our objective function, f. Here we define f to be this expression. We can write the 2 norm as the product of the vector transpose times the vector itself to get the following expression. We then set the gradient equal to 0, leading to the normal equations given here. And we'll see that x is equal to the pseudo-inverse of a times b is the mathematical equation. However, this does not behave well numerically. This is since a transpose a has condition number double that of a itself. The condition number is the ratio of the largest to smallest singular values of a matrix. To calculate this condition number, we can use the singular value decomposition to find the singular values. So we also will talk about matrix factorizations such as the SVD and eigenvalue decomposition, which can be useful for stability analysis. Note that for a positive definite matrix, the eigenvalues are equivalent to the singular values of a matrix. The eigenvalue decomposition will be useful when we want to compute powers of a matrix. Note that it is only defined for square matrices. So going back to this least square system, if we don't want to directly solve the normal equations, what matrix factorization can we use here? We will see that the QR factorization can be used to simplify the equation to only an upper triangular solve, which is very efficient.